Welcome to Cognito Key. Today, we're going to dive into the microscopic magic that powers literally every single device you use. We're talking about the very heart of all modern electronics. So what is the secret? Well, the answer lies in a really special material. You could call them the unsung heroes at the heart of all our modern tech. Let's take a closer look at how they work. So in this explainer, we're going to break it down into 5 simple parts. We'll start with what a semiconductor is, then look at its pure atomic structure. After that, we'll get into the recipe for conduction, check out the 2 key flavors, and finally, wrap up with the big picture.
All right, first things first. What exactly is this crucial material that has completely changed our world?
Okay, so think of it this way. You have conductors, right? Like a copper wire, electricity flows through that super easily. Then you have insulators, like rubber, which stop electricity completely. A semiconductor, it sits right in the middle. It's not a great conductor, but it's not a great insulator either. And that's its superpower. Its ability to conduct electricity can be controlled very, very precisely. So, as you can see right here, semiconductors are in this unique sweet spot. Now, this in-between property, it's not magic. The real secret is deep inside their atomic structure. So to really get it, we need to zoom way in, right down to the atomic level of a pure semiconductor. And the technical term for that, by the way, is an intrinsic semiconductor.
So we're mostly talking about elements like silicon, the silicon in Silicon Valley, of course, and also germanium. Now, what's interesting is that both of these are found in group 4 of the periodic table, and that's not a coincidence. That location gives them a really important property.
And that special property is they each have exactly 4 electrons in their outermost shell. See, in the world of atoms, 8 is kind of the magic number for stability. Every atom really wants to have 8 electrons in that outer shell to feel, complete and stable.
So how do they get to that magic number 8? Well, they form partnerships. Each silicon atom shares one of its 4 electrons with each of its 4 neighbors. It's like they're all holding hands, creating these things called covalent bonds. And this makes a super stable, repeating crystal structure where every single atom is connected. Now, in this pure state, the intrinsic state, remember, the material is actually a terrible conductor. And why is that? It's because all the electrons are busy. They're locked into these bonds, holding hands with their neighbors. There's just no free electrons to move around and carry a current. Okay, so if they're such bad conductors when they're pure, how on earth do we make them useful for electronics? Well, this is where things get really clever. We change the recipe using a process called doping. So what is doping? It's basically the process of deliberately adding a tiny, tiny amount of an impurity, a different element, into that pure crystal. And when I say tiny, I mean it. We're talking about maybe 1 single impurity atom for every 10 million semiconductor atoms. It's almost nothing. But this tiny change completely transforms the material's properties. This doped material is now what we call an extrinsic semiconductor. And depending on what kind of impurity we add, it comes in 2 really important flavors. And those 2 flavors are N-type and P-type. So let's look at how each one is made and what makes them so different from each other. Okay, let's start with N-type. To make this, we add an impurity from group 5 of the periodic table, something like arsenic. Now, these atoms have 5 electrons in their outer shell. So when an arsenic atom takes the place of a silicon atom in the crystal, 4 of its electrons form bonds with the neighbors, just like they're supposed to. But that leaves 1 extra electron just hanging around with nowhere to go.
And this leftover electron? It's now totally free to move around the crystal, which means it can carry an electrical current. Because that impurity atom donated a free electron, we call it a donor impurity. And since electrons have a negative charge, well, you guessed it, the material is called N-type, for negative.
All right, so what about P-type? Well, for P-type, we do the exact opposite. We add an impurity from group 3, like gallium, which only has 3 outer electrons. So when this atom joins the crystal, it can only form 3 bonds with its neighbors. And that leaves one of the silicon's bonds incomplete, creating an empty spot where an electron should be. This empty spot is what we call a hole, and it acts just like a positive charge. A nearby electron can easily jump into this hole, and when it does, it leaves a new hole behind. So it looks like the hole itself is moving. Because this impurity atom created a space that can accept an electron, we call it an acceptor. And since the hole behaves like a positive charge, the material is called P-type, for positive. So this table sums it up perfectly. N-type has extra free electrons, P-type has extra holes, or spaces for electrons. They're basically two sides of the same coin, and that's what makes them so incredibly powerful when we put them together.
Okay, so let's get to the big picture. We've gone to all this trouble to create materials with extra electrons and materials with extra spaces for electrons. So, why? Why does any of this matter?
Let's do a quick recap. We started with pure semiconductors, pretty useless as conductors. Then we used doping to create N-type materials with free electrons and P-type materials with these holes. But the real magic, the thing that our entire digital world is built on, happens when we combine them. By putting N-type and P-type materials together, we can create the tiny, microscopic switches, the transistors and diodes that power everything.
Seriously, think about it. Everything from a simple LED light to the most powerful AI supercomputer is built on this one elegant idea. These are the basic building blocks of our modern world. And that leaves us with a really exciting question. If these are the simple blocks, what incredible structures can we build with them next?
So if you found this useful and want to keep unlocking more key concepts with us, please do me a favor and like this video, share it with someone who's curious, and of course, subscribe to Cognito Key for more. Thank you so much for watching.